So in this video, we're going to look at properties of determinants under matrix operations. So here we have a series of claims about determinants of matrices to which matrix operations are being applied, like multiplication by a scalar, product of matrices, transpose, inverse of matrices. So let A and B be n by n matrices. So we're letting A and B be square matrices of the same size. So the determinants exist and the products exist. C is a scalar, and we know that means that C is just an element of the real numbers. And so here are the four claims that are being made. If we have a scalar multiple times A, so if we multiply C times the matrix A, distribute C into all of the elements of A, then the determinant of C times A will just be C to the n times A. The proof of this actually would be pretty simple. You would take and apply the property of determinants. Remember, we have a property of determinants that says if B comes from A, from matrix A, by multiplying any single row or column by a scalar C, then we learned that the determinant of B was equal to C times the determinant of A. That was what you got if you multiplied a single row or column by a scalar C. So if we're multiplying C times the matrix A, we're multiplying every row of A by C. So we apply this idea repeatedly, and we would get C to the n because there are n rows. Each row that we got, we would get C times the determinant of the previous matrix. So we get C to the n times the determinant of A. This one says that the determinant of a product of two matrices is equal to the product of the determinants. This one says that the determinant of a transpose is the same as the determinant of A. You'll be asked to prove this one in the homework. Don't go to Proof Wiki and just copy the proof from the internet into the homework. This has happened now on 2 of the homeworks, and 1 of the take-home exams. I've had students copying Proof Wiki proofs that I bet they couldn't explain to me if I asked them to, but this has happened. Don't do it. This proof here is not going to be a hard one. Think about how you calculate a determinant, and then think about what the transpose of a matrix looks like, right? The rows become the columns become the rows. So this proof should be pretty easy. You'll get to do it in the homework. And this one says that if you want the determinant of the inverse of a matrix, it's just going to be 1 divided by the determinant of the matrix A. And the proof of this would actually be driven by property 2. So if you'd already proven this one, which I thought about making you prove in the homework, but I went ahead and deleted it, and I put this one in because it's easier. But this one, if you have property 2 in your pocket, this proof's pretty easy, because what you do is you consider the product A times A inverse. Right, you let A inverse, you let B from property 2 equal A inverse, and then you do A times A inverse, and you know that A times A inverse is just the identity matrix. So if this is an n by n, if these are n by n matrices, then you're going to have the identity matrix for n by n matrices, and you're going to get this matrix as it has a bunch of 1s on the column, and it's going to turn out that if you calculate the determinant of an identity matrix, you just get the product of the main diagonal. So you get 1 times 1 times 1 times 1. So it turns out that it's pretty easy to show that the determinant of the identity matrix is just equal to 1. And then you apply property 2 here, where it says, hey, the determinant of a product is equal to the product of the determinants. So you use that to say, hey, this can be broken like this. And because the determinant is just a number, you just divide both sides by the determinant of A to get 1 over the determinant of A. So the proof of 4 relies on 2 things. It relies on property 2 right here, and then it relies on being able to demonstrate that the determinant of an identity matrix is equal to 1. And this would be pretty easy to prove. We won't prove it right now, but we do have some concepts coming up very quickly. I think actually in this homework, in this set of videos, that would allow us to prove this trivially. So anyways, here are the matrix properties. In the next video, we'll apply these properties to calculate the determinants of some matrices.